nature of electrodes. Nature of electrode. How does it affect electrolysis? Or how does it affect migration of an ion? Electrode can either be reactive or what? Unreactive. Unreactive electrodes are called what? Unreactive electrodes are also called inerts. There are two electrodes that will affect discharge of ions. There are electrodes that when you use them, the electrode will tend to inhibit the reaction. Inhibition means stop the reaction. Or even if it's not stopping it, it will slow the reaction down. Okay? Whenever you're using a reactive electrode like copper is very reactive. Copper electrode, or using zinc electrode, or using iron electrode, or using mercury electrode. These electrodes are going to basically affect whatever ions that will be what? Discharged. Whenever you're using electrodes, so these are examples of what? Reactive, or active electrode. Okay? Whenever you're using platinum or what? Carbon, in form, not just carbon, but in form of what? In form of what? Graphites. The two are not reactive. They are not going to affect discharge of ion. Supposing, let's look at this, electrolysis of CuSO4, dilute CuSO4 aqueous. Supposing we are using copper electrode, not platinum electrode. I've shown you what happens when we use platinum. Let's see what happens when we use copper. Let's see how copper will affect the electrolytic reaction here. Okay, I will just use the setup quickly. I have here usually my what? Anode, and here my what? Cathode. Let me label it. Cathode and what? Anode. So what will be my electrolytes? Copper 2 tetraoxosulfate 6. It appears that the whole color here of this solution here is what? Is what? Blue. That's the color of copper 2. Hydrated copper 2 is what? Blue in color. Anyway, now what we're using here is copper electrode. Solid. The solid here. Copper electrode solid. So it appears solid. Okay? You still have copper here as well. That is from the salt, from the electrolyte. You have copper that may try to get itself discharged here. That's where it's going. Sorry. Copper that will get itself discharged at the what? Anode. Cathode. And then you have another ion which may try to discharge itself there. This one. Sorry, before this one. OH from water, because this one will always be down. The one that will go discharge will go up. That is the principle. This one will easily come up, okay, and get itself discharged, because this one is more mobile than this, being lower in the series. Then that means H from water remains. These are the ions from here. As when you add water to this electrolysis, this electrolyte, add water to this. The electrolysis process will be like this. This will be ions present. But no, normally, if these electrodes are not active, you see this going here, and you see this going here. But that will not happen in this reaction, because the copper here will not allow copper here to react. Rather, copper here will come out from the plates, because it's reactive. And before you know it, the copper goes into this solution and reduce this ion from this copper and form copper what? 2. And form what? Copper 2. As simple as that. And once that happens, copper from here appears to be impure. This is one way you can apply electrolysis. This is pure case of what? Purification of metal. I want to purify this metal, this particular metal. Let's say I have a metal that is very, very impure. Maybe this metal has just 44% copper. I want it to be up to 98% copper. What I will do, I will purify it. And for me to purify it, I want to make this impure copper to be my what? Anode. is going to be my anode by force. And all the copper in it, that is 44%, will all come out here with impurities. The impurities will go alongside with this. All impurities will tend to dissolve in the solution. They will come and then eventually become what? Become what? A slag. Then copper going, this copper moving again can move with this. So this I already have dissolved. The copper now going out from the solution is no longer 44%, but closing to what? 90 to 98%. So the copper goes out again, second time. And then coming here, the copper too, from this plate. So when the copper left this particular plate, what happened to the size of this anode? Is it going to increase or decrease? In fact, it will do what? It will decrease. That is how it will look like. Because much mass of copper has left this particular electrode. Goes in here, come here, and once it goes here, it's going to gain electron from this particular electrode. And immediately it does that, it will now what? It will not reduce by losing that what? Electron. Then copper here appears to be solid. Okay? It appears to be what? Solid. But it gains 2 electrons, and then in each solution, what happened to the copper there? It oxidizes in this solution before going to the side. On getting here, it gains this electron and then what? Reduce to what? To what? Metallic copper. What happened to the mass of the cathode when it gets deposited here? Will it increase or decrease? It will increase now. It has entered here. From here to here, the mass of where it's coming from will decrease. The mass of where it will deposit will do what? Increase. And anytime one is electrolyzing or purifying a metal like copper, okay, you must make the anode the impure. The metal you want to purify must be the anode. And you must use electrolytes of the what? Of the metal you want to purify. Let's say you want to purify silver. You can use copper salts to purify silver, where you are using silver impure here. So the salts you must use as electrolyte must be a sort of silver, preferably silver trioxo nitrified. But since I'm purifying copper, I'm using what? An electrolyte of that salt, of that metal I want to what? Purify, which is copper 2 tetraoxosulfate what? 6. If this electrolysis happens to be that of electrolysis using inert electrode, copper, all the copper in the solution will migrate to the cathode, isn't it? And then the whole of this particular solution will, the blue solution here will tend to what? Disappear or fade, because copper will discharge. But in this case, copper in these salts did not discharge. It remains in the electrolyte. It remains. So it means that the color of this copper will not disappear. Rather, it will what? Persists. You know what I mean? Persists. Because copper is still here. That is the only copper that is reacting is copper from the what? Plate or electrode. So more of the copper in the ionic salts were allowed to migrate because the electrode has now interfered with the what? Migration of ions. That means all these ions are still here. At the end, what will be the nature of your electrolytes? What will be your nature? Nature is that the electrolyte remains what? The same. Because nothing has changed. No copper from here migrates. So the only thing you see here is copper from the plate goes into solution, do one or two things, leave behind some impurities, and then left, and then get inside the deposit here. That means the copper from the ionic salt still remains where it is. So in this case, the electrolyte remains unchanged. Are you with me? And then the color of the solution still persists or remains what? The same. That is, if you are talking of electrolysis of copper 2 tetraoxosulfate using a reactive electrode like copper. But if it is an electrode of copper 2 sulfate using graphite or carbon or platinum, the moment this electrolysis happens, the moment the copper migrates to the cathode, the solution, the blue color of that solution, of that electrolyte, will tend to what? Fade or disappear. Am I communicating? Am I communicating? So this is to say that whenever an electrolyte change or tend to be reactive, it interferes with the electrolyte. Okay? Whenever it is not reactive, it will just stay and just be a spectator. It will not even take part in the reaction. It is just there to allow how electrons goes in or go out.